Imagine a tower stretching from Earth to space, a colossal structure that defies the limits of human engineering and imagination. A structure so tall it seems to touch the stars, piercing the night sky with its grandeur and ambition. This is the dream of a space tower, a seemingly simple concept with incredible appeal. It captures the imagination of scientists, engineers, and dreamers alike. Such a structure could revolutionize space travel, making the journey to the stars as routine as a flight across the globe. It could make access to space cheaper and easier, opening up the final frontier to more people than ever before. We could transport people and cargo with less risk and expense, transforming how we think about space logistics and exploration. However, the reality of building a space tower is far more complicated than the dream. The engineering challenges are staggering. The challenges of building such a structure are immense, involving unprecedented levels of precision and innovation. They range from material science to the very nature of our planet, each presenting unique obstacles that must be overcome. The first hurdle is finding a material strong enough to support the tower's weight, a task that pushes the boundaries of current technology. This is where the dream begins to crumble, as the harsh realities of physics and engineering come into play. No known material possesses the necessary strength to build a space tower. The concept of constructing such a colossal structure has fascinated scientists and engineers for decades. The tower's weight would be astronomical, literally. The sheer mass of the materials required would be beyond anything we've ever handled. Even the strongest materials like steel and titanium would buckle under their own weight long before reaching space. These materials, while incredibly strong, have their limits. Some have proposed using advanced materials like carbon nanotubes. These materials are at the forefront of material science research. Carbon nanotubes are incredibly strong for their weight. Their unique structure gives them unparalleled strength and flexibility. They are much stronger than steel. In fact, they are considered one of the strongest materials known to man. However, even these futuristic materials fall short. The challenges of building a space tower are not just about strength, but also about the ability to withstand various forces. The immense height of a space tower creates forces that exceed the capabilities of any known material. The higher the structure, the greater the forces it must endure. The problem lies in the concept of tensile strength. This is a critical factor in determining whether a material can be used for such a project. Tensile strength is the ability of a material to resist being pulled apart. It is a measure of how much force a material can withstand before breaking. A space tower would experience unimaginable tensile stress. The forces pulling on the structure would be immense and constant. The weight of the structure pulling on itself would be too great. This is the fundamental challenge that must be overcome to make the dream of a space tower a reality. The weight of a space tower wouldn't just stress the structure itself, it would also have a significant impact on the Earth's crust. The base of the tower would need to be incredibly large to distribute the weight. Even then, the pressure exerted on the Earth's crust would be immense. This pressure could have devastating consequences. It could lead to the ground sinking or even cracking. The Earth's crust is not a solid, unyielding surface. It is a dynamic layer floating on a molten mantle. The weight of a space tower could disrupt the delicate balance of our planet's geology. We live on a rotating planet. This rotation creates centrifugal force. Centrifugal force is the outward force experienced by an object moving in a circle. In the case of a space tower, centrifugal force would act sideways on the structure. The taller the tower, the greater the centrifugal force. At the tower's peak, the centrifugal force would be immense. This lateral force, combined with the tower's already immense weight, would create a recipe for disaster. The tower wouldn't just buckle under its weight, it would be ripped apart by the forces of Earth's rotation. Even if we could overcome the challenges of material strength and Earth's rotation, we would still face the unpredictable fury of nature. A space tower would be exposed to the full force of Earth's weather systems. Wind, rain, storms, and temperature fluctuations would constantly batter the structure. Hurricanes and tornadoes could tear the tower apart. Lightning strikes could cause significant damage. Even seemingly minor weather events could have a cumulative effect. Over time, the constant exposure to the elements would weaken the tower, making it more susceptible to catastrophic failure. Space is not empty, it is filled with millions of pieces of debris ranging from tiny flecks of paint to defunct satellites. These objects travel at incredibly high speeds. Even a small piece of debris can cause significant damage upon impact. A space tower would be a giant target for this space debris. Collisions would be inevitable. Over time, these impacts would weaken the tower's structure. While we can track larger objects and potentially move a tower out of their path, smaller debris is much harder to monitor. These smaller impacts, happening constantly over time, would slowly but surely wear down even the strongest structure. The construction of a space tower would be a logistical nightmare. The amount of material needed would be staggering. We would need to develop entirely new methods for transporting and assembling materials at such heights. Even if we could overcome all the other challenges, the sheer scale of the project makes it almost unimaginable with our current technology. The risks involved in such a construction project would be enormous. The potential for loss of life and resources is simply too great. Responsible engineering requires us to acknowledge these risks and explore alternative solutions. While a tower to space seems impossible, a related concept offers a glimmer of hope: the space elevator. This idea, though it sounds like science fiction, is grounded in real scientific principles and engineering possibilities. Instead of a rigid tower, a space elevator would use a cable anchored to Earth and extending beyond geostationary orbit. This cable would need to be incredibly strong and lightweight, far surpassing the capabilities of any material we currently possess. This cable would be held taut by centrifugal force with a counterweight at its end. The counterweight would balance the forces acting on the cable, ensuring it remains stable and secure. Specialized climbers could then ascend and descend the cable, transporting people and cargo to and from space. These climbers would be powered by advanced propulsion systems, making the journey efficient and relatively quick. The space elevator concept still faces significant challenges, primarily related to material strength and space debris mitigation. Scientists and engineers are exploring new materials like carbon nanotubes and graphene, which might one day make this dream a reality. However, it represents a more plausible path to achieving our space travel ambitions. By reducing the cost and complexity of reaching orbit, a space elevator could revolutionize our approach to space exploration and development. While it may remain a dream for now, the space elevator reminds us that even the seemingly impossible can become possible with continued innovation and a spirit of exploration. It stands as a beacon of hope, inspiring future generations to reach for the stars.